It's well known that Euler's formula maps any real number theta representing radians to a point on the unit circle on the complex plane with the horizontal coordinate cosine theta and the vertical coordinate sine theta. In the formula, e is the Euler number, which is the base of the natural logarithm, I is the imaginary unit, and sine theta and cosine theta are the trigonometric functions of sine and cosine. This formula looks strange at first glance. Let's look at the definition of trigonometric functions for a right triangle. For an acute angle, theta of a right triangle, the angle is between 0 and 90 degrees. Its opposite side is A, the adjacent side is B, and the hypotenuse is C. According to the Pythagorean theorem, a square plus b square equals c square. Sine theta is defined as the ratio of the opposite side to the hypotenuse, a divided by c, and cosine theta is defined as the ratio of the adjacent side to the hypotenuse, b divided by c. Because the opposite side and the adjacent side are smaller than the hypotenuse, both sine theta and cosine theta are greater than 0 and less than 1. We can use the unit circle on Cartesian coordinates to expand the definition of trigonometric functions. For points a, b on the unit circle with a radius of 1, the range of values of a and b is from -1 to +1, inclusive. Theta is the length of the arc from point 1, 0 on the horizontal axis to point A, B, which has directionality. If it is counterclockwise, theta greater than 0. If it is clockwise, theta less than 0. Sine theta is defined as A and cosine theta is defined as B. In this way, we expand the range of values of sine and cosine functions from the open interval 0, 1 to the closed interval -1, 1. In particular, sine pi divided by 2 equals 1, sine pi equals 0, sine 3 pi divided by 2 equals -1, sine 0 equals 0, corresponding to the 4 intersection points of the coordinate axis and the unit circle. The period of sine x and cosine x is 2 pi, which is the circumference of the unit circle. It can be seen that if the image of the cosine function is translated to the right by 1/2 plus 2n times pi, or translated to the left by 3/2 plus 2n times pi, the image of the sine function is obtained. The definition of the nth power of the imaginary number I is as follows. I to the power of 0 is equal to 1, corresponding to the point 1, 0. Rotate it 90 degrees counterclockwise to get I to the power of 1. I to the power of 1 is equal to I, corresponding to the point 0, 1. Rotate it 90 degrees counterclockwise to get I to the power of 2. I to the power of 2 is equal to -1, corresponding to the point -1, 0. Rotate it 90 degrees counterclockwise to get I to the power of 3. I to the power of 3 is equal to I, corresponding to the point 0, -1. Rotate it 90 degrees counterclockwise to get I to the power of 4. I to the power of 4 is equal to I to the power of 0, which is equal to 1, corresponding to the point 1, 0. Just back to the starting point. Therefore, for any natural number n, I to the power of n is equal to I to the power of n plus 4. Multiplying I to the power of n by I is equivalent to rotating the corresponding point 90 degrees counterclockwise around the origin. Each point will return to the starting point after 4 90 degrees rotations. Obviously, Euler's formula is closely related to exponential functions. Let's first look at how to calculate exponential functions. For the case where the exponent is an integer n, just multiply the target by n times. For example, to get 2 to the 10th power, multiply 2 10 times to get 1024. To get e to the 10th power, multiply e 10 times to get 22,026.4658. What if the exponent x is a rational number? For example, how to compute e to the power of square root of 2? In fact, the exponential function is defined by Taylor expansion. E to the power of x is defined as 1 plus x squared divided by factorial of 2, plus x cubed divided by factorial of 3, etc. Obviously, the derivative of this function at any position is equal to itself. In fact, if the derivative of a function is equal to itself, then the function must be a constant multiplied by e to the power of x. In particular, e to the power of 0 equals 1, e to the power of 1 is approximately equal to 2.718218, which is the base of the natural logarithm, also called the Euler number. To derive Euler's formula, we need to know the Taylor expansion of trigonometric functions. To derive the Taylor expansion of trigonometric functions, we need to know their nth order derivatives. The first order derivative of sine x is equal to cosine x. The the second-order derivative of sine x is equal to negative sine x. The third-order derivative of sine x is equal to negative cosine x. The fourth-order derivative of sine x is equal to sine x, and the cycle starts here. Therefore, the nth-order derivative of sine x is equal to its n plus fourth-order derivative. In order to finally derive the Taylor expansion of the sine function, it is necessary to further calculate the nth-order derivative of sine x at 0. The first-order derivative of sine x at 0 is equal to 1. The second-order derivative at 0 is equal to 0. The third-order derivative at 0 is equal to negative 1. The fourth-order derivative at 0 is equal to 0. According to Taylor's formula, sine x equals x minus x to the power of 3 divided by factorial of 3 plus x to the power of 5 divided by factorial of 5 minus x to the power of 7 divided by factorial of 7 plus each term contains odd powers of x alternating between positive and negative. With the Taylor expansion of sine x, it is much easier to derive the Taylor expansion of cosine x because cosine x is equal to the first-order derivative of sine x. It can be seen that cosine x is the sum of items containing x to the power of evens alternating between positive and negative. The left side of Euler's formula is a complex exponential function. Using the complex number I multiplied by x to replace the real variable x in the exponential function, we get the expanded form of Euler's formula. Since the even power of I is equal to plus or minus 1, and the odd power of I is equal to plus or minus I, we put the terms on the right side of the equal sign containing even powers of I multiplied by x in one group A, and the terms containing odd powers of I multiplied by x in another group B. After simplification, each term in B is only I multiplied by a real number, which can be extracted. Finally, we get e to the power of I multiplied by x's equal to cosine x plus I multiplied by sine x. This is the origin of Euler's formula. Let's look at a special case of Euler's formula. Euler's identity, that is, the case where theta is equal to pi, e to the power of I times pi equals minus 1, representing the point minus 1, 0 on the complex plane. Another more common form of its representation is e to the power of I times pi, plus 1 equals 0. Euler's identity contains 5 most basic mathematical constants. Pi, ratio of a circle's circumference to its diameter, approximately equal to 3.141596. E, Euler number, the base of natural logarithms, approximately equal to 2.71828. I, imaginary identity, I squared equals negative minus 1. 0, additive identity. 1, multiplicative identity. Euler's identity may contain some of the most basic laws in the universe and is known as the most beautiful formula in mathematics, as shown in the animation as theta increases from 0. First, the point projected onto the unit circle after the Euler formula transformation rotates counterclockwise around the origin from 1, 0, and returns to the starting point after 2 pi radians. Second, the function sin theta changes periodically from 0 synchronously, and the period is also 2 pi. For consistency, we overlap the point 1, 0 on the left complex plane coordinates with the origin 0, 0 on the right Cartesian coordinates. Finally, let's look at what the multiplication of two complex exponentials means. From this equation, we can see that the multiplication of 2 points on the unit circle on the complex plane is equivalent to the addition of their corresponding 2 radians. That is, the point A corresponding to the real number alpha radians multiplied by the point B corresponding to beta radians is equivalent to rotating point A counterclockwise around the origin by beta radians. The point B corresponding to the real number beta radians multiplied by the point A corresponding to alpha radians is equivalent to rotating point B counterclockwise around the origin by alpha radians. It's well known that Euler's formula maps any real number theta representing radians to a point on the unit circle on the complex plane with the horizontal coordinate cosine theta and the vertical coordinate sine theta. In the formula, e is the Euler number, which is the base of the natural logarithm, I is the imaginary unit, and sine theta and cosine theta are the trigonometric functions of sine and cosine. This formula looks strange at first glance, as it links complex exponential functions with trigonometric functions. How did it come about?